In Control Systems Lecture 2, we are going to learn two graphical models: block diagrams and signal flow graphs. This slide shows you the topics to be covered by this lecture. First, I will introduce you what a block diagram is. Then, I'll explain how to simplify a complicated block diagram. The second graphical model we are going to learn in this lecture is called the signal flow graph. To have a good understanding of signal flow graph, we must learn Mason's gain formula. Then I'll give a number of examples to show block diagrams and signal flow graphs. The last point on this slide is the introduction of a number of MATLAB functions used for system modeling. And I'll leave that part to yourself because the best way to do well in MATLAB is practice, practice, and practice. That's exactly what the common saying goes: practice makes perfect. We have learned in the previous lecture that to model a physical control system, we can write out a set of differential equations. The best way to deal with differential equations, we use Laplace transform in the context of control systems, because the Laplace transform converts differential equations into algebraic equations. And we know that transfer function is defined as the ratio of the Laplace transform of the output to the Laplace transform of the input. And we always assume zero initial conditions whenever we derive a transfer function for a system. For control systems, the input variable and the output variable is related by transfer function. And this relationship we know is called the input-output relationship. In order to show this input-output relationship in a graphical way, which is more straightforward, we commonly use block diagram or signal flow graph. A block diagram consists of unidirectional functional blocks that represent the transfer function of the variables of interest. On the slide, you see a simple block diagram, and this block diagram depicts the input and output relationship of a field-controlled DC motor and its load. Compared to a set of abstract mathematical representation, a block diagram shows the relationship of the variables in the system in a more straightforward manner. And that is exactly the beauty of the graphical models. Suppose we have a system which has two inputs and two outputs. The two outputs are Y1s and Y2s, and the two inputs are R1s and R2s. If we use mathematical equations to describe this system, we see this. By the look of it, it is hard to see the relationships between the inputs and the outputs. Even if we write this in matrix form, which looks more compact, it is still not that obvious to see the relationships between the input variables and the output variables. However, if we draw the block diagram of this system, everything becomes more clear. The two input variables are R1s and R2s. The two output variables are Y1s and Y2s. And the relationships between them can be easily seen from this block diagram. Now, let's look at the derivation of the closed-loop transfer function of a feedback control system. This is a general block diagram of a negative feedback control system. When I mention the word negative, it means the negative sign here. Of course, we may also have positive feedback control system, but in this subject, we only focus on negative feedback control systems. So the task here is to derive the transfer function Cs over Rs. And the system is depicted by a block diagram. How do we do this? We know that Cs is equal to Gs multiplied by Es. We just follow the signal flows in the system. But just to have this is not enough, because we want to find the relationship between Cs and Rs. Therefore, Rs must come into the picture. Rs is related to Es by this equation. Es is equal to Rs minus Bs. And then we further go on until we find the relationship between Cs and Rs. So all these steps are intermediate steps. Once we find relationship between Cs and Rs, we need to write it in the transfer function format. That is Cs over Rs. And this is our result. So Cs over Rs is equal to Gs over 1 plus GHS. This transfer function is called the closed-loop transfer function of this feedback control system. And this is what we will be using very often in the rest of the semester. I would like also to mention 1 HS is 1. We call the system a unity feedback system. When GS times HS is greater than 1, we say Cs over Rs, or the closed-loop transfer function, is approximately equal to 1 over HS. That is, the relationship between the input and output is mainly defined by HS, which is the feedback loop component. And this is an important attribute of a feedback control system. This paragraph shows what I just mentioned. An advantage of closed-loop systems over open-loop systems is that closed-loop systems allow the system performance to be dominated by the components in the feedback path, which was clearly shown in the previous slide. This is important because some components in the forward path may be beyond designer's control. But the components in the feedback path is always within the designer's control. I would like to give you an exercise for you to practice at home. And the exercise is to find the transfer function Es over Rs. It is the same feedback control system which was shown in the previous slide. But now the transfer function I'm asking you to determine is Es over Rs. Please do this as your homework. I will show you the solution in the tutorial. Now let's look at how we can simplify a block diagram. this slide shows you the methods that can be used when we reduce a complicated block diagram. The general principle to follow is that the transfer function before and after block diagram reduction should remain unchanged. We can see that if we have cascading blocks, we can just multiply them together. And then if we have a summing point here, we can move it after the block G. And the rest, you can look at them by yourself. To prove what I just said, the transfer function before and after block diagram reduction should remain unchanged. I'll randomly pick up a reduction method and show you why it is the case. Let's just use this one. So this is to move a summing point ahead of a block. So the summing point is moved to a point ahead of G. X3 equals X1G. Let's use the plus sign here. Plus X2. This is before. And after block diagram reduction, the relationship becomes X3. Again, we just use the plus sign. It becomes X1 plus, here we need to consider the loading factor. It becomes X2 multiplied by 1 on G bracket times G. And you can say that these two are equivalent. Therefore, the general principle is exactly followed. And let me repeat the principle. The relationship between the input and output before and after the block diagram reduction should remain unchanged. And the last one on this slide is what we have just derived in the previous slide, the closed loop transfer function. Now let me give you an example of the simplification of a complicated block diagram. So this example shows you a multi-loop feedback control system. Our goal is to find the transfer function Ys over Rs. This is our goal. How do we approach this problem? First, we can say we have several loops. In this example, we have loop 1, we have loop 2, and we have this big loop, which I call loop 3. So the first step is we need to clear these loops. How do we do this? Loop 1 and loop 2 are interlocked. Therefore, we need to move this point after block G4. That is what has been done here. And now you can say that loop 1 and loop 2 are clean loops. Therefore, we can reduce this loop. We can reduce this loop, L2. So L2 now has become just one block because we have reduced it. And then after doing this, we can see that this loop can also be removed. And now it becomes a single block. After that, we only have one big loop left. And then we can reduce it to get to the final solution.